So in this video, I wanted to present some work that we delivered at EUSIPCO in 2019 in Spain. Now, I want you to imagine this use case. So Nuanced Communication run a service where they'll convert voicemails into text messages. It's obviously very useful if you're in a meeting or if you're in a noisy environment and you can't really listen to the voicemail message. You can read the text message instead. Now that uses ASR, automatic speech recognition, to do that, to convert the speech into text. But because Nuance are obviously dealing a lot with these voicemail messages, it would be quite nice to know what is the quality of the speech of those messages. On average, let's say, how good does the speech normally sound in a voicemail recording? Well, we only have access, obviously, to the voicemail message, so is there a way that we can estimate this speech quality? Well, why don't we start then? That's the sort of motivation. Why don't we start by looking at this overview of speech quality estimation and where it arises from? So way back in the past, when people started to assess speech quality, they would just use listening tests. They would get lots of listeners to listen to a recording. They would get them to rate it, the recording quality, that is, the speech quality in the recording, from 1 to 5. So 1 would be dreadful and sort of inaudible, and 5 would be impeccable, perfect. And everyone would give it a score. You would average all of those scores from all of those listeners, and you would get what's called the MUS score, the mean opinion score. And that was how people used to do it. It's a subjective way, it's very accurate, it's actually measuring the right thing. But obviously it's very expensive. If you have to have lots of listeners doing this, you have to pay them. Also, it takes a lot of time because they've all got to listen to these recordings to give you a score. So because of this, obviously objective methods were developed. So these were methods that used an algorithm instead. You no longer needed the listener. Now, of course, they're less accurate. They might not be quite evaluating the right thing. However, they're quick, they're fast, they're easy. You can run them on vast amounts of data. So in the days of machine learning and big data, obviously these are the things that we need. These are the tools we need. We need to be able to evaluate speech quality without the need of listening tests, because it's just impractical in most situations. We couldn't get a listener to listen to thousands of hours of voicemail recordings to evaluate, for example. Well, how do objective methods work? They use an algorithm, as I said, but there's actually two types. So the first type that sort of got developed were what was called intrusive methods. They required the clean speech signal and the degraded speech signal. And what you would do is you would do an auditory transform on the two of them, and then you would compare the dissimilarity. Now, obviously, that was quite a good way of doing it. The problem is now you need the clean reference signal, which in our case of voicemail messages, you don't have the clean signal, you only have the degraded signal. So all these methods that required the clean signal and the degraded signal, these intrusive methods, aren't actually practical for most real-time and real-world applications. They're only practical for sort of simulations and testing. So that's why non-intrusive methods were developed. And these methods only required the degraded signal. And that's basically what we developed in this work. We developed a way of estimating, actually, an intrusive method. So as you can see from the title, it's the estimation of POLQA. POLQA stands for Perceptual Objective Listening Quality Assessment. And we basically estimate the POLQA score using a machine learning method. And therefore, POLQA now becomes non-intrusive. There are a few other benefits as well, but that's the main aim, that we've now made POLQA non-intrusive. The nice thing about this is obviously we can get lots of data. We can train it on POLQA because we'll have the clean speech, and we can degrade the clean speech by some sort of noise and room impulse responses, some codecs, and then we can train our neural network to estimate that POLQA score. And then we have a non-intrusive POLQA estimator, which is basically what we did here. So if I just move down the poster, then I'll show you the proposed system that we developed. So here it is, and the first part, if you look on the left-hand side, is basically all of this, before these little circular blue balls. All of that is how we developed the features to our neural network. So what features were we going to use to estimate the POLQA score? Well, we used two. We used the commonly MFCCs, dimensions were 24, which are normally called lossless MFCCs in narrowband case. And we also used modulation features. So how do we develop the modulation features? Or let's say, did we get the modulation features? Well, as you can see from the diagram, we took the FFT and then the FFT again, and then we get the modulation spectrum. Now, a lot of people do different things with this modulation spectrum to try and encapsulate or encode that information in a small number of coefficients. So a lot of people look at energies and things like that, but a higher level feature, because obviously you can't put the spectrum directly into the neural network really in a practical sense. So what we did to solve this problem is, it was actually Wang's work at Cambridge, he's now at Cambridge, was to do a 2D DCT. And that basically, as you can see from the spectrum in the poster, it sort of removes most of the information. It sort of shrinks it down. You can see that most of it's now down here in the spectrum. So now we can just take the first 24 coefficients of the DCT, and that gives us our modulation features. So it's a good way of encapsulating the data that's embedded in that spectrum. So now we pass that to a neural network topology. And the neural network topology is an LSTM, a recurrent neural network topology. LSTM stands for long short-term memory. Now the reason for that is because each frame we're getting 48 features, 24 MSCCs and 24 modulation features. But obviously we don't want to give a POLQA score for every frame, because that would be silly, because they're only 10 millisecond frames. We want to have a much larger context window, or temporal window, where we evaluate. So in this case, in a lot of our testing, we picked 30 frames. So we took 30 frames and we evaluated the POLQA score over those 30 frames, or we tried to estimate the POLQA score from those 30 frames. And that's why you need an LSTM, because actually all of those frames matter to give you the POLQA score. It's not like the later frames matter more than the earlier frames. And the long short-term memory, the idea behind it is you can store in memory information that you saw a long time ago. So even if you saw the information in the first frame, when you get to the 29th frame, you can still, the information in the 0th frame is just as important, or can be just as important in the neural network, because it can store that in memory. So that's why an LSTM was used. And as you can see from the topology, in the example, this would be obviously frame 0 going up to frame 29. So we pass in our 48 features, we pass in 30 frames of context, and then we pass it through 3 layers of LSTMs, 3 layers of an LSTM network. In each layer, as you can see down here, the topology was 40, so there's 40 cells in this particular, so each one of these is 1 frame. So we have our input 48, then we have 40 LSTM cells in this block here, then 21 in this one, and then 16 in this one. And each of these blocks obviously has an output going to the right and then an output going up. So the output going up is obviously storing the time information. So this is obviously frame 0, this is frame 1, all the way up to frame 29. And then this is obviously going to the output when it goes right. Now there's a few things that we added in. So to try and sort of reduce the noise, we did do some regularization, which basically is this dropout here in the 3rd layer. It's actually between the 2nd layer and the 3rd layer. So we ran this network for 10 epochs, and in the first epoch, the dropout rate was 75%. So we dropped 25% of the connections between the 2nd layer and the 3rd layer. Another thing we did was we took the last 10 frames at the output. So this output of each of these blocks would be 16, but we actually averaged the last 10 frames, not just the last one. And then we fully connect those with the 2 nodes at the output that I'll come to in a sec. And that was another regularization. It's not standard, but it's a way that if we don't just take the last frame, then we get less noise in our output if we just average over the last 10. Then what are the 2 outputs then? So we've been talking a lot about POLQA, which is the Perceptual Objective Listening Quality Assessment, that's the word, the speech quality estimator. But we also estimated something else. So we had basically a VAD. We got the mean voiced posterior, I think is what we called it in this paper. But actually that's just a score from 0 to 1, telling us the probability that the frame is voiced. Obviously POLQA is irrelevant if it's not speech. So we want to know whether we should keep this sort of window of context or we should discard it. So we prune away windows that basically, or temporal regions that don't contain speech, and we only want to include in our evaluation the ones that do contain speech, and then we care about the POLQA score for those particular regions. Just to give you some more information that's probably not in the paper, is the ReLU was used as the activation functions for all of these outputs, and we use the the root mean squared error as the cost function. And the way that we obviously normalize these outputs is because POLQA goes between 1 and 5, and obviously the probability that Framer's voice is 0 to 1. We subtracted 1 from the POLQA score and then divided by 4 to normalize it between 0 and 1. So we could use that cost function. So that's basically the topology for the network that we trained it on. Just to give you a bit of the idea of the data, I'll scroll down here. So we took 100 hours of training data, and we took speech from the Libra corpus, Libra speech corpus. And then we convolved those bits of speech with rim impulse responses. We basically generated lots of rim impulse responses from the image source method, and they were between they had a certain T60 and a certain C50, as you can see there. So all of the rim impulse responses met that criteria. And then we just sampled one and used it on the speech. We convolved it with the speech. Then we added some noise. You can see the different types of noise. We had ambient, babble, household, street, and vehicle noise. And again, the SNR for that noise was between 0 and 30 dB, which is obviously what we'd normally see in real-world situations. And then because we're looking at voicemail messages predominantly, we ran it through different mobile phone codecs. So we had 10 different codecs, or conditions for codecs. So we had 100 hours of speech that we could train it on. So we basically ran all of this 100 hours of degraded speech on actual POLQA and got real POLQA scores for that data. So now, and we also, because Libra speech gives you ground truth, we also ran it on an algorithm that's in the paper to get the probability that the frame is voiced. So now we have our two outputs. We have the ground truth POLQA score, and we have the ground truth mean voice posterior score given by the other algorithm. So now we can train our network to try and estimate these two scores. And then we obviously tested it, and we tested it generating the data in the same way. The only difference is we didn't use any of the same speech, or the same rim impulse responses, or the same noise. So that's the main difference. And there was slightly less rim impulse responses used, slightly less noise sources used, because we only had 15 hours rather than 100. And the different speech signals that we used were the clean partition from the Libra speech corpus, and we used English, French, and Japanese from the ITU-T P23 corpus. So we actually tried to see if it would generalize well across languages, because we thought that would be quite interesting. So we train it on English, but does it work well on other languages as well? So these are our results. So the first thing I should mention is on the left we have a graph. Now all that's trying to show is how well does it work if we take different temporal window sizes. So if we include more frames than just 30. So the reason that I mentioned 30 is because 30 gave us the lowest error. So that's the one we used for the actual results here that you see in the table. But it actually really doesn't matter if you want to take 30 frames of context, or if you want to take 50, or even 80, or even 120, the score doesn't really the error doesn't really increase that much. As long as it's above 30 frames, it's quite good. Another thing that this shows is a previous PESC estimator, which was presented at Global SIP in 2014 by Duchamp. Actually, that's an utterance-based method, performs worse in all situations. Obviously, that doesn't have a frame. There's no understanding of frames there, so it's only plotted here just to prove that it's worse for any size, any number of frames for the other method. But this is utterance-based, so that's why you don't see any change by the frame size, because that doesn't mean anything. But it's nice to compare that even when you have 10 frames, the utterance-based method is still actually worse. So that's basically what we used as our baseline, because there aren't any other methods that estimate POLQA or PESC in this non-intrusive way. So what results did we get? Well, as you can see, we list the results for just using MFCC features and for MFCCs and these modulation features. And you can see that when we use both features together, we actually get quite good results. So the mean absolute difference is 0.21. And so for most applications, I think that would be more than fine. It depends how accurate a POLQA score you actually need. And the VAD F1 score gives you 0.9, which is extremely good. And actually, if I go back to this graph, you can see that our proposed method is in green if we actually use our our fully proposed method. But actually, obviously, as I said, we prune away regions of unvoiced, unvoiced regions, basically where there's no speech, because we don't want to evaluate the POLQA score at those points. So if we prune away those ones based on the output from our algorithm, then we get the green one. But actually, if we just use the ground truth from the method that we use to generate those mean voice posteriors, then actually the difference is only about 11% improvement. So actually that proves how good our method is at estimating VAD, that actually even if we use the ground truth VAD, it doesn't make that much difference to the error. It makes it slightly better, but not massively better. And as you can see, you can look in your own time. But what is interesting is the languages that we haven't seen actually generalize extremely well. So Japanese, for example, here performs better than the English, which is surprising. I don't know if that's something to do with the recording or just Japanese lends itself to speech quality assessment, but it's interesting to see that actually Japanese performs extremely well, even though it's never seen Japanese in the training. So it generalizes well also across methods. So that's basically what this paper represents. It represents a way of estimating POLQA in a non-intrusive manner. It works extremely well if you use this LSTM topology. We also showed how we could compress the information of the modulation spectrum into modulation coefficients using this 2D DCT, which is actually a novel way of doing the compression of that information in the modulation spectrum. So we have this novel modulation feature. And as you can see, we get extremely good accuracy for both the POLQA and the VAD. So hopefully you found this work interesting. Hopefully it's helpful having me explain it. But yeah, thank you for listening. If you have any questions, do feel free to email me. I'll be happy to answer. Thank you.